Everybody, I'm going to be talking about NMR and equivalent protons and carbons in NMR in this video. So generally, every unique proton or carbon environment is going to result in a peak in the NMR. Okay, so that's kind of what we're thinking about here. So unique environments equal peaks. Most of the time, the number of the peaks is going to match the number of the unique environments. Okay, it can be complicated by overlapping peaks if you think about two peaks that have a very close chemical shift, which we will get to, and they start sitting on top of each other, they're going to be obscuring that, so it's not going to be able to be counted quite as cleanly. But for the most part, usually the number of peaks is going to equal the number of unique environments. So when we're looking at kind of the just summary of an NMR, and I'll be popping this up in the following videos as well, just so that we kind of get used to seeing it. This is how NMR data is presented if you're not given an NMR spectrum. I will usually be giving you this and a spectrum just so that you have the summary and the actual visual. But when we're looking at equivalent protons and carbons, we are really looking at how many of these do we have. So in this case, we've got 3, where we're thinking about kind of an A peak here, and a B peak here, and a C peak there with 3 total proton environments. Okay, in this case, we're seeing peaks. We are not quite sure if those are peaks or environments, but it's going to be a pretty safe assumption, and that's what actually looking at the spectrum can really help you with as well. In the carbon, you're just counting the numbers. Okay, so in this case, we've got 4 carbon peaks. Okay, so that's telling us how many different environments we have present in this molecule. So to really identify what are going to be equivalent protons, we really need to be looking at symmetry. So I have these 3 that I'm going to be doing as examples here. I'm going to stop the share real quick so that I can show you my models that I made. Okay, so this first one is going to be the one that was on the left-hand side of the screen. It's the ether that has the tert-butyl groups on it. So when we're looking at symmetry here, there's a couple things that you kind of want to notice. So anytime that we've got a group of 3, so that would be like a methyl group, tert-butyl group, anytime you've got 3 of the same things, whether they're methyls, they're H's, when we think about the process of this molecule just at normal kind of spin, there's not going to be any visible difference between that methyl, or that methyl. Okay, so that's going to be any time that we have just a single 3. So same up here, right? These H's are all going to be experiencing the same things as they spin around this molecule. So that's one thing that we need to keep in mind. Second thing is identifying planes of symmetry. So in this molecule, we've got a plane of symmetry right here, right? When we're looking at that, that means that this carbon is reflecting into this carbon into this one, and then these 3 and these 3 are all in the same environment. Okay, so that's kind of the planes of symmetry that we're looking at for that one. When we're looking at our hexane here that we've got as the second example, it's just like we would talked about in the chirality section. It's hard to see planes of symmetry when you're like this. What you can see is you can see that we've got a plane of symmetry down the backbone. I actually get things lined up correctly. Okay, we do have a plane of symmetry down the backbone where we're seeing these hydrogens reflecting into each other. So that's something to note, that these 2 H's are being reflected in that plane of symmetry there. So those are going to be the same environment. Okay? They are not going to be registering as a unique environment because they're seeing all the same things. But for the rest of the chain, you want to be getting this chain into a more symmetrical, viewable shape to see if there's any other planes of symmetry that we should be looking at in terms of what's reflecting side to side. So same type of process, we're going to go and do our rotation so that we get more of that U shape. So now we're looking at something that's at least symmetrical with the backbone. And then we can see that we do have a plane of symmetry right here, where we've got that carbon and that carbon are going to be in the same environments, this one and this one in the same environments, and these two in the same environments. So when we get to something cyclic, right, we can have this situation, and we actually do have a plane of symmetry right here, right? It's cutting into the plane of the molecule. So it is telling us that our two H's and two H's and two H's, that those are, you know, that to that is the same, that to that is the same, that to that is the same. But we don't have any other planes of symmetry here in terms of the rest of the molecule. So if we look at what that looks like in two. Screen share was not set up right. We got it. Okay, so if we look at what that actually breaks down to when we have our individual pieces on paper, okay, we can kind of think about the fact that we saw that plane of symmetry right here. And so when we look at that, we can kind of just start looking at one half of that molecule and recognizing that any of the H's that I have over here are mirrored on that other side. Okay, and also recognizing that all of the H's that we have on the methyls of that terbutyl group are all going to be in that same environment because of the 3 and the spinning. Okay, so because we have that free rotation and we've got all those hydrogens that are seeing all the same things, those are all going to be one environment. So if we look at this in total, we've got an environment A there, and then B, and these are all the same. On the other side of the molecule, that is again mirrored by these A's and our B's. Okay, so we've got, oh dang. Let me pause this so I can get that changed into the right color so I can color code. Okay, now I've got it color coded again for purple is proton. So I only have 2 proton environments or peaks in this entire molecule. Okay, if we do a similar type of analysis for our carbons, we're seeing again in that same little box is mirrored on the other side. So we've got a carbon here, a carbon there, and then we've got these 3 carbons. So this carbon doesn't have a match in the box. This one doesn't have a match in the box. But again, those 3 are going to be just like our H's, where because they're just 3 on the same carbon, they're going to be rotating around. So for our carbons, we've got 1, 2, and 3. Okay, so 3 carbon peaks. And again, those are mirrored on our other side, where we have the same 1, 2, 3 carbon peaks as well. Keep in mind that don't let carbons that don't have hydrogens psych you out. They are going to be showing up in your carbon NMR. They will not be showing up in your proton NMR because they have no protons on them. Okay, so then we have this next one. We did do a little conformation change first, and that got us to something that looked like this. Once we're there, we can again see that we have that plane symmetry here. We can draw our little box, and in that box is really all we need to be worrying about. And our protons, if I draw those in real fast, this is again going to be a really good time for you to practice that skill of drawing in your hydrogens. Okay, so my protons, I've got 1, 2, 3 on those carbons. So I've got an A, B, and C. And again, all 3 of these are in that same environment because they're just kind of rotating and spinning over there. And then we did see that on A and on B, they are both mirroring each other through a plane of symmetry in the backbone of this molecule. Okay, so we've got 3 proton peaks or environments here. Then we can go look at our carbons. And we've got 1, 2, 3 carbons. So we're going to have 3 carbon environments there as well. And that's going to be all mirrored on the other side, as well as our protons with the ABC and 1, 2, 3. And then we have even matches. Okay, keeping in mind that these two are mirroring each other, these two mirroring, and then these two mirror. For our last example, we've got the only plane of symmetry is actually in the plane of the screen right now. So when we're looking at our protons, we can draw those in. And we saw in the model that the 2 H's on each carbon are both mirroring each other in terms of the wedge dash. But we don't have any other mirrors in terms of splitting this molecule. So when we're looking at protons, we're going to be looking at A, B, and C for all those 3 environments. And then for carbons, again, we don't want to be forgetting carbons just because they don't have any hydrogens on them. We've got a carbon of our ketone, and then the CH2 there, the CH2 there, and the CH2 there. And again, none of them are equivalent because they are not mirroring anything else. So 4 carbon environments there. Okay. When you get to benzene, in a way, it gets easier because it is flat, right? I'm going to switch to that real quick. Okay, so when you're looking at benzene, you've got something that's flat. So when you're looking from the side, you always are going to have this plane. What we're more concerned with is what kind of planes we have actually cutting through the ring. And you could either be cutting through bonds, so like bonds like this, or atoms. Okay, so in the case of this, you'd have a plane of symmetry right here. If I went and changed to something like that, I would still have a plane of symmetry right there, right? Because I can line this up so that it is going to be mirroring itself no matter kind of what I have over here. We're going to have that plane of symmetry right there. So important to note that when we're working with the actual double bonds, those are not counting towards the symmetry because we are thinking about this as our full resonance delocalized hybrid, right? Where it's just all delocalized in here. So the double bonds don't count in that symmetry breakdown. Okay. Okay, so that means that when we're working with 2 identical substituents, we can see a plane of symmetry right here. And if I have an ortho substitution pattern, which this is our ortho, where I have something on the 1 and 2 positions, I can again do that same kind of situation or move where I make my little box, draw my hydrogens, and then we can see that we're going to have 2 proton environments and 3 carbon environments. And again, they're mirrored over here, so our identical ones are going to be like that. Okay, the meta, which is the 1, 3, we've got a plane of symmetry right here. So we're going to have a little diagonal box. So since this box is going through atoms and not bonds, we want to be keeping in mind that the H that is on that, any H's that are on the line of that symmetry still need to be counted, and the carbons as well. Okay, and we just want to be noting that because they're being split by that line of symmetry or that mirror plane, that they're not getting reflected anywhere, so those are going to be unique positions. So I've got H here and H here as well. So then I can go and look at my H's and say that I've got an A, B, and C. And then carbons, 1, 2, 3, 4, where 2 and 3 are mirroring each other. And for our protons, we've got B as a mirrored proton. Okay. For para, which is the 1, 4 substitution, you want to look at this one carefully because I've got a plane of symmetry right here, but I also have a plane of symmetry perpendicular to that right there. So in this one, I'm actually looking at a much smaller piece of this box where I only have one H in it. Okay, so keep that in mind just to make sure that you're finding all of those planes of symmetry. It's going to be important. So we really only have the one proton environment here. If I look at carbons, I'm going to have a little bit more. I've got a 1 and a 2, but I only need to be working inside that box because this is also a carbon 1, that's also a carbon 1, and that's also a carbon 1. Our carbon 2 is right over here. Okay. When we're thinking about our protons, we just got A protons all over the place. Okay. So our carbons, we've got 2 carbon peaks. It gets a little bit more complicated on benzene when you're looking at 2 different substituents, but it's not too bad because we're still working with flat. We can see that if I don't have the same substituent on this ring, I don't have any mirror plane besides the one that just cuts through all of the atoms, which is not very helpful here. In both my ortho and my meta examples. Okay, so if I don't have any mirror plane there, they're all going to be unique environments. So in that case, I'm going to have 4 proton peaks and 6 carbon peaks. Okay, because we don't have any planes of symmetry, they're all unique. And that's going to be the same over here, where I've got the 6 carbon environments and the 4 proton environments. When we get to the para substitution, now that we have them kind of lined up on the diagonal there, now we can think about doing a plane of symmetry. So we can have that, with that being our little box. And then we've got the 2 H's. So we've got an A and a B proton environment. So we've got 2 proton peaks. And then for our carbons, we need to count everything on the line or in the box. 1, 2, 3, 4 for the 4 carbon peaks, okay? With 2 and 3 mirroring, and then your A and B protons over there as well. Okay, so this definitely takes practice. Use model kits if you need to. It's going to take a little bit of time to get used to it, but just use your model kits, find those planes of symmetry, and count up how many unique environments you're going to have. Alrighty, let me know if you have any questions, and I'll see you all later.